Welcome to our channel Circuits Analytica. In this video, we will be discussing about inverting amplifier. The open loop gain of an operational amplifier is ideally infinite, and typical value of open loop gain is 10 raised to 6. The output voltage of an opamp is V0 is equal to VID into AOL, where VID is the differential input voltage and AOL is the open loop gain of the operational amplifier. A very small differential input voltage VID leads to a saturated output when the operational amplifier is in open loop. To overcome the problem of saturated output, the gain of the opamp must be reduced. That is, negative feedback must be used to reduce gain. With negative feedback, a part of the output voltage is fed back to the inverting input of the operational amplifier through a feedback network. With feedback, the opamp is said to be in closed loop as there is a closed loop between output terminal and inverting input of the operational amplifier. In closed loop, if input is applied to the inverting input of the opamp, then that becomes an inverting amplifier. If input signal is applied to the non-inverting input of the opamp, then that becomes a non-inverting amplifier. So this is the diagram of an inverting amplifier. So here the non-inverting input is connected to ground. Input signal Vin is applied to the inverting input of the operational amplifier through resistance R1. So a resistance RF is connected between the output and inverting input of the operational amplifier, which provides feedback. So here, the closed loop gain of the circuit depends only on the resistors R1 and RF. Let us consider an ideal opamp. So in open loop configuration, output voltage V0 is written as V0 is equal to AOL into VID, as open loop voltage gain AOL is defined as the ratio of output voltage to differential input voltage. So AOL is the open loop gain and VID is the differential input voltage. VID is equal to V1 minus V2, where V1 is the voltage at the non-inverting input and V2 is the notation for voltage at the inverting input. So for an ideal opamp in open loop, voltage gain AOL is infinite. So output voltage V0 is equal to AOL into VID. That means open loop gain AOL is equal to V0 divided by VID, that is equal to infinite. That means VID is equal to 0. Differential input voltage VID is defined as the difference between voltage at the non-inverting and inverting inputs. VID is equal to V1 minus V2. So VID is equal to 0 means V1 minus V2 is equal to 0. That means V1 is equal to V2. So for an ideal opamp, voltage at the non-inverting input is same as the voltage at the inverting input. V1 is equal to V2. Now let us discuss the concept of virtual ground. So this virtual ground exists in inverting amplifiers. So for an ideal op-amp, VID is equal to 0. That means V1 is equal to V2. For an inverting amplifier, as non-inverting input is connected to ground, V1 is equal to 0. So V1 is equal to 0 means V2 is also equal to 0. Potential at the inverting input of the inverting amplifier is equal to 0. And this condition is called virtual ground. So the potential at the inverting input is equal to 0. So even though it is not connected to ground. So this concept is called as virtual ground. Now we will find gain of an inverting amplifier. So I1 is the current flow towards non-inverting input of the op-amp and I2 is the current flow towards inverting input of the op-amp. In is the current flow through resistance R1 and IF is the current flow through feedback resistance RF. We know that for an ideal operational amplifier, input impedance is infinite. So input impedance is the impedance between inverting input and non-inverting input of the operational amplifier. Input impedance is equal to infinity means these two terminals are perfectly open. That means current flow towards non-inverting input is equal to 0. Similarly, current flow towards inverting input is also equal to 0. Apply Kirchhoff's current law at the inverting input of the operational amplifier. So at the inverting input of the operational amplifier, there are three currents associated with the inverting input. And the three currents are I-in, I2 and IF. So here, I-in is an incoming current and I2 and IF are outgoing currents. That means, according to KCL, I-in is equal to I2 plus IF. So KCL states that total incoming current is equal to total outgoing currents. I-in is equal to I2 plus IF. So as input impedance Rin is infinite, I2 is equal to 0. So equation 1 becomes I-in is equal to IF. Now let us write expressions for I-in and IF. I-in is equal to VR1 divided by R1. That means I-in is equal to V-in minus V2 divided by R1. This is equation number 2. Similarly, we can write IF is equal to VRF divided by RF. IF is equal to V2 minus V0 divided by RF. Equation number 3. So I-in is equal to IF from equation 1. V-in minus V2 divided by R1 is equal to V2 minus V0 divided by RF. From equations 2 and 3. So V2 is equal to 0 as the inverting input is existing at virtual ground. So put V2 is equal to 0 in this equation. We will get V-in divided by R1 is equal to V0 divided by RF. So we can write closed loop voltage gain AF is equal to V0 divided by V-in, that is equal to minus RF divided by R1. So gain of the operational amplifier in inverting mode or gain of an inverting amplifier is AF is equal to minus RF divided by R1. Thanks for watching Circuits Analytica. Enjoy learning. Please comment, share and subscribe our channel.